So, we are discussing about modeling of the flow of a falling film. I will once again tell you the salient feature of the problem that we are trying to model. It is a liquid which is in contact with an inclined plate and it is falling while maintaining a constant thickness of delta on the solid plate. The coordinate system is drawn in such a way that in the direction of flow it is z, across the depth of the fluid it is x, and this is the y direction. So, the velocity changes only in the x direction, it does not change in the z direction or it does not change in the y direction. So, we are imagining a shell of some thickness delta x in the flow field, which is aligned in the flow field. The length of this shell is L and the width of this shell is W. These two are constants. So, there would be one face which is perpendicular to the flow. So, if this is my imaginary shell, this face is going to be perpendicular to the flow. So, across this face mass is going to enter the control volume. Across this face mass is going to leave the control volume. There would be no mass flow rate across this face or these two faces, the bottom and the top faces. So, convective flow of fluid can only take place through these two faces. So, we have written the expressions for the amount of flow that comes in, the amount of the mass that comes in, and the momentum that comes in. Since the velocity is not a function of z, so therefore, these two terms in and out by convection will cancel each other. We also understand the velocity at this point and the velocity at this point are different, because this is my x direction and somewhere over here I have my solid plate. So, velocity over here is more as compared to the velocity over here, because as I approach towards the solid plate the velocity decreases, and on the solid plate because of no slip condition it just becomes equal to 0. So, since there is a variation in velocity from Newton's law of viscosity, from the concept of viscosity, I know that there exists a shear stress on the top surface and on the bottom surface. If the fluid is Newtonian, that means if it follows Newton's law, you can simply express the shear stress as mu, the viscosity of the liquid, multiplied by the variation, by the gradient of velocity at this point. So, you have a Vz varying with x. So, the gradient is simply going to be dVz dx. You are evaluating it at x, and over here the gradient expression would remain the same. Only thing is you are evaluating it as x plus delta x. So, the molecular transport of momentum is simply going to be mu velocity gradient multiplied by the area. What is this area? It has a length equal to L and then width equal to W. So, the area on which the molecular transport that is taking place is L times W. So, that is what I have written over here is L times W is the area, and this is tau x z evaluated at x and tau x z evaluated at x plus delta x. So, this is essentially the molecular transport of momentum. Okay. So, I have a convective part and a molecular part which are acting on it. There is also a gravity force which is acting on this surface. So, on this control volume, this is again my control volume of thickness delta x, length L, and the width is W. So, the mass of the liquid which is contained in the volume, which is L W delta x, this is the volume of the fluid inside the control volume. I multiply it with rho in order to get the mass of the control volume, and cos beta, which is g cos beta, which is the component of the body force. So this totally gives me whatever be the force which is acting on this system. Now this is my z direction, this is my x direction, and somewhere over here is my y direction. So this gives me the body force which is existing, which is acting on the control, on the imaginary control volume. So if I write the momentum balance equation now, it simply becomes LW tau xz at x, which is molecular transport of momentum in, minus LW tau xz at x plus del x, which is molecular transport of momentum out of the control volume, plus W del x rho Vz square at z equals 0, which is the convective transport of momentum into the system, and this is convective transport of momentum out of the system, plus sum of all forces acting on it, and the only force here is the gravity, which is this. Since it is at steady state, all these forces, the algebraic sum of all these forces must be equal to 0. So I have defined a control volume, identified all the sources of momentum that can come into the system, and I have also identified the only relevant component of force present in the system. I identify that it is the body force which is present in the system. There is no surface force, because it is a freely falling film. So the pressure on both sides are the same. So now I have a complete equation. Now if you see this equation has delta x in it. Okay, so it's an expression which is valid over this control volume defined by W, L, and delta x. So what I am going to do next is cancel the terms which are not relevant, which cancel out each other, for in this case the convective flow of momentum, and divide both sides by del x and take in the limit when del x approaches 0. And you would see that this would lead to the definition of the first derivative, and from this difference equation I would be able to obtain the differential equation. So let us see what happens when we divide both sides by del x. We identify here that v at x equals 0, v at z equals 0 is equal to v at z equals L. So this term and this term would cancel out, and then I divide both sides by del x. So what I am going to get here then is and cancel out the LW from here as well. And I bring this del x from here over this point, and I take the limit when del x tends to 0. So this entire thing, this equation that I have written, is a statement of the physics of the process, and what I have done over here is the definition of the first derivative. So what you get out of this is simply d dx of tau xz is equal to rho g cos beta. So what you can see here is that from this difference equation I get the definition of the first derivative, and when I use the definition of the first derivative, what I get is a differential equation that that governs, that essentially gives me some idea of what is, how the shear stress is changing and how it's balanced by the body forces. So I integrate it once, which would give rise to rho g cos beta x plus C1, where C1 is the constant of integration. And I understand that at liquid gas interface, tau xz must be equal to 0. So this is the plate, this is my film, here is x, and this is x equal to 0, and this is x equal to delta. So what it tells me is that at x equal to 0, tau xz is 0. It's a direct correlation, direct relation from direct observation from the liquid gas interface. The shear stress would be 0, which we have explained before. So starting with the governing equation, using the appropriate boundary conditions should give me a compact form, analytical form of velocity, and that is what we would like to do here. If this is 0, then this should give me C1 to be equal to 0, and your tau xz would simply be rho g cos beta times x. Now, if I assume that this is a Newtonian fluid, Newtonian liquid, then what I am going to get is tau xz is equal to minus mu dvz by dx. I can write the normal ordinary derivatives because my vz is a function of x only. My vz is not a function of z or a function of y. So this is truly a one dimensional flow. Had this been a 2-dimensional flow or a 3-dimensional flow, then the system would be more complicated, and you won't be able to solve it in this simple way. But this simple approach essentially gives us an idea about this modeling process, a simple modeling process, wherein by identifying the shell, identifying the contributions of momentum, convective, diffusive or molecular transport, and the body forces, would give rise to a governing equation that can be solved to obtain a compact equation for the velocity, as in this case. So we start with this. So when you substitute it in here, what you are going to get is dvz by dx is minus rho g cos beta by mu times x. You integrate it once again, you get vz rho g cos beta by mu times x square by 2 plus C2, where C2 is another integration constant. Now, in order to solve C2, we use the second boundary condition, which is no slip. And what does no slip tells us is that at x equals delta, that means at the solid liquid interface. So this is my x and this is delta, this is z, and right. So at x equals delta, that means on this solid liquid interface, my velocity must be equal to 0, which is known as the no slip condition. So when you put that in here and you solve for C2 and substitute it into this equation once again, what you get is Vz as rho g del square cos beta by 2 mu times 1 minus x by delta whole square. Now I have what we have set out to do from the very beginning. I have an expression for velocity, and this expression for velocity contains several parameters. So if we think intuitively, the velocity is going to be maximum at the liquid air interface, and the velocity is going to be minimum, 0 in this case, at the liquid solid interface, and in between the velocity varies. When you look at the functional form of the velocity variation, you would see that the variation is parabolic in nature. So, therefore, if you plot the velocity, it is going to be something like this. So, the velocity varies from 0 to some v max at x equals 0. This is x equals delta. So, the velocity reaches the maximum over here, and in between it follows a parabolic path. So, at x equals 0, you get your Vz to be the max, which would be rho g del square cos beta by 2 mu. Whenever you solve an equation, model a system and solve an equation, you should always try to see if it is consistent with the physics of the process. So, let us see what happens if you increase beta. That means, if you increase the angle of inclination, if you increase beta, the velocity has to increase, which is clear over here. If for a constant system geometry, if you decrease the value of mu, the velocity increases. So, that means a lesser viscous fluid will flow faster along an incline in compared to a thicker to a more dense or a more viscous fluid. So, that is also there. And further you are from the solid plate, the velocity increases. So, this gives you with some idea of what is going to be the velocity, the velocity and the maximum velocity in the system. But in many cases, as engineer, you are not interested in to know what is the maximum velocity or how the velocity varies between the solid plate up to the liquid interface, liquid gas interface. You are more interested to know what is the average velocity. So, in order to obtain the average velocity, there are different ways by which you can average to find out the velocity. The most common and logical way to do this averaging is if you average across the flow cross section, because across this flow cross section, across this, the velocity varies from 0 over here to Vz max at this point. So, this is the cross section in which the velocity varies. So, you really need to find out an area average of the velocity, area average of the point velocity in order to find what is the average velocity. So, all the average velocities that we are going to refer from now on will be area average velocity, whereas the area across which I am averaging is perpendicular to the principal direction of flow. So, here the principal direction of flow is in the z direction. So, it is an area which is perpendicular to the z direction. So, it is the z face across which I am doing the integration, with my understanding that the velocity varies with x, it does not vary with y. So, even though I am using a double integration in order to average it across the z face, across y it does not vary, across x it does vary. So, the expression for the average velocity mathematically would be Vz dx dy, and here also it is dx dy, that is the area. And if you see that x varies from 0 to delta, which is the thickness of the film, whereas y is the width of the film. So, it varies from 0 to w. So, it is from 0 to w for y and 0 to delta for x. And when you do this integration, of course, the y be, since Vx does not depend on y. So, you can take this out, and your Vz would simply be equals to 1 by delta, is from 0 to delta Vz dx, and the expression of z you are going to plug it in from the previous one, and what you would get is rho g del square cos beta by 3 mu. And once you have the average velocity, this denotes the average velocity, and then you would also like to know what is the film thick what is the volumetric flow rate. So, this is the volumetric flow rate, and the volumetric flow rate would simply be W delta times Vz. So, this is the cross sectional area through which this is taking place. So, your Q becomes rho G W del Q cos beta by 3 mu. So, you can see that starting with a very fundamental concept, that momentum in, rate of momentum in minus rate of momentum out plus sum of all forces acting on the system at steady state must be equal to 0. When you use that concept and define a control volume, the smaller size would be denoted by the direction in which the flow is changing. In this case, flow is changing with the x direction. So, therefore, you have delta x as one of the dimensions of the control volume, and you write that. You also identify that we are dealing with the simplest possible case, which is one dimensional flow. So, velocity is a function of x, it is not a function of z or a function of y. You divide both sides by del x, use the definition of first derivative, and what you get is a differential equation. Use solve the differential equation with boundary conditions, no slip and no shear. You get a compact expression for velocity. Once you have the expression for velocity, then you would be able to obtain the average velocity and the total volumetric flow rate. So, that can be obtained. One part that I haven't described, we haven't done as yet, is what is the force exerted by the moving fluid on the solid. If you think, you can clearly see that the force exerted by the fluid on the plate, the force is in a direction perpendicular to the motion. So, the motion is in this place, but the force gets transferred from the liquid to the solid in this direction, and since it is moving, it would try to take the plate along with it. So, in order to keep the plate stationary, you must apply a force in the reverse direction, because the fluid flow would try to take the plate along with it. So, what is the force? What is the genesis of the force? It must be due to the viscosity. So, the viscosity of the liquid, the shear stress out of this viscosity is essentially shear stress exerted on the top area of the solid plate is the one which is the force exerted by the liquid on the plate. So, what is the area on which it is acting on? It must be equal to the length times width of the plate, LW. What is the shear stress? It is tau. The shear stress is simply going to be equal to tau xz. So, the shear stress is tau xz and it is acting on an area equal to W times L. So, if I need to find out the total force total force exerted by the fluid on the solid plate, I need to integrate this tau xz over dz and dw, and the limits on z and L, the limits on z must be equal to 0 to L, and the limits on w would be limits on y would be 0 to w. So, if I do perform this one, I would be able to get an expression for what is the force exerted by the fluid on the solid plate, and the solid plate in turn gives the same thing back to the fluid. So, let us figure out what is, let us find out what is the force exerted on the plate by the fluid. So, Z component of force let us call it as F of the fluid on the surface it is in the z direction from 0 to L, from 0 to W, tau x z. Remember that we have to evaluate this shear stress at x equals delta, because that is where it is acting. This is the liquid and this is at x equals delta dy dz. So, this is the same as for tau minus mu times dvz dx at z equals at x equals delta dy dz. It would be equal to rho g delta cos beta L times W. This is the force in the x direction. So, this is interesting. What you see here is that this expression is nothing but the z component of the weight of the entire fluid or entire fluid present in the film on the plate. So, this gives you, and there is no mu in here. Okay. So, this entire thing tells you that the force exerted force of the fluid on the surface is simply the weight of the fluid contained in the film. So, that is another interesting result. Whenever we talk about this kind of simple modeling, we must also be aware of the limits imposed by our simplified treatment. The first thing is it is only valid for it is not valid for very fast flow, it is only valid for laminar flow. If you do have turbulent flow, if the liquid is moving at a very high velocity, then you are going to get waves at the top, and which would probably not be able to use the concept that it is zero shear at the liquid vapor interface and so on. And we have also assumed that it is one dimensional flow with straight streamlines. If it is 2-dimensional flow or a 3-dimensional flow, then this simple analysis would not be, you would not be able to use. And finally, whether or not it is laminar flow or turbulent flow, you would be able to obtain that. You will be able to get an idea by calculating what is the Reynolds number for the flow. And for certain range of Reynolds number, lower values of Reynolds number, this analysis is perfectly valid. And this is an ideal example to show how it can be done. The other complexity that we did not consider, let us say that solid plate on which the inclined plate on which the flow takes place is at an elevated temperature. If it is at an elevated temperature, then the viscosity that we have used to express the shear stress using Newton's law of viscosity, that tau is equal to mu times the velocity gradient, that mu would also be a function of x. So, mu near the plate, since the temperature is more, would be lower as compared to the mu near the top. So, this variation in the physical property, the transport properties of the system can cause additional problems, and you won't be able to obtain such a closed form simplified solution. If you also have, if you have the plate at a higher temperature, then that could set in, that will set in heat transfer across the film as well. So, not only the thermophysical properties would vary, the temperature would vary, as a result of which the flow field, the velocity field would be different than what we have done here. So, this is just a tiny baby step that we took in this class towards understanding fluid flow, towards trying to see how the shell momentum balance in the simplest possible term can be used to find out what is the velocity field. But the real life is much more complex. As we progress in this course, we will try to model, simulate situations which are closer to the reality, and this course should teach all of you the tools to analyze such real life problems ultimately.